Good afternoon. Thank you for coming to the SETI Talk today. We are going to get started. Our speaker today is Orkan Umurhan. Orkan was educated at UCLA and at Columbia University, and since then he's worked on a number of research topics. Among other things, he is part of the science team for the New Horizons spacecraft at Pluto, which is dear to the hearts of us here at the Institute. But his primary focus of research has been protoplanetary disks, and particularly the role of turbulence in shaping the environment for these baby solar systems. And that's what he's going to be talking to us about today, the enigma of planet formation. Let's welcome Orkan Umurhan.
Thank you. Thanks. Okay, so let me get started with this. First of all, you might notice there in the thanks list, I left off, there looks like there's one more name in there, and that's actually Jeff Moore's name. I just got so quick, I was running behind schedule, and I forgot to add his name on there. So anyway, so thank you for being here. What I'd like to do is I'd like to talk to you today about recent developments in the story of turbulence and its role in the development of planetesimals in our solar system and in all other young solar systems that we have observed. And so the main issue is the role of turbulence and how it mitigates and or brings about the collection of particles and disks, because it's the missing link. And today I'm going to report to you on some recent developments regarding that. So let me break this up into essentially two parts here. And the first part of this talk will be pretty short, and I'm just going to give you a basic background on growing planets and planet-forming disks. And the broad overview here is that I will break it down to a story about disks in general and their observational overview. The origins of planets and observational constraints. I'm not going to propose a definitive storyline here, but I will give you what are considered agreed upon observational constraints. And then I'm going to talk about a little bit more dynamics of the particle growth mechanisms in the presence of turbulence. The second part of the talk, and this is where I've done a lot of extensive research on, is the question of dynamics within disks. So I'll give you a little bit of background on the dynamics of disks themselves and why it's such a subtle problem. And then I'm going to talk about the both old and new disk turbulence mechanisms. Okay, so as some of you in the audience have been a party to these latest discoveries of direct imaging of planets around debris disks. Here's an example of Beta Pictoris, and this is results of the last few years where we have direct imaging of planets orbiting the central star. So you see here the extended disk on either side, and this is what's called the debris disk phase of planetary disk evolution. And so just to give you kind of a flavor of what it is that we're dealing with and what it is, in what medium we're trying to sort out how planets are formed. This is quite nice, and I do have to thank Kevin Zonley yesterday over coffee. He did point out, I've been at a meeting last couple of weeks, and in that period of time, this new image to the right was actually posted by a group who had done VLA observations of the famous H.L. Tall disk, which was imaged by ALMA in the millimeter range. And let me first discuss, broadly speaking, you see that this is a late-ish stage disk in which you actually see structure forming in the form of rings in the disk. These are gaps that are being driven open. Number of mechanisms that are proposed to explain the origin of the gaps. Could be planets sweeping them open. It could be actual dynamical instabilities within the gas itself. So those are open questions right now, but it's pretty tantalizing and mouthwatering to see this quality and resolved image of a disk that had been, and these disks, of course, had been known to exist were surmised to exist up to, as far as 50 years ago from spectroscopic measurements. And in the last 15 to 20 years, we've had tremendous progress in direct imaging of these objects, so it's quite exciting. And if you look to the right, you'll see that there's the same ALMA image, and overlaying is the VLA image, which is a high-resolution image of the inner part of that disk. And you can see very clear structure emerging in the interior part of the disk. This is brand spanking new. This is March 23rd was released. So there's a lot of people are scratching their heads, trying, I'm sure, and there's a lot of my fellow theorists that are already banging out theories for why this is what we see. So this is a story that's far from over. Here's an image. This is a classic many of you have seen of what are called proplids. And these are very young disks in which the gas is very thick. And you see them distributed in all over star-forming regions. And these are essentially the young embryos of disks in the process of eventually turning into solar systems of one form or the other. So here is the issue. How does one go from star formation then on to the next stage, which is the planetary disk, or the proplid stage, and then eventually down to planets? And I am biased. Pluto is a planet, in my opinion. Not to scale, of course. And so how do we get there? That's the big open question. And this has concerned theorists and observationalists and scientists for over 30 to 40 years. I mean, people, of course, solar system and its origins have been the question of mankind for as far as we have been keeping stories. But from the scientific point of view, great progress has been made in the last 30 to 40 years on that. Just want to point out that whatever processes that are taking place, they're taking place within the first 100 million years after the primary star has actually come into place. So just to put this into context, if the solar system is a 46-year-old adult, the solar system has matured into a face that looks something like what we see today, with a little bit of afterbirth floating around after 1 year. So that's kind of the formation process, and all that activity is happening on that relatively short time scale. Very short by geologic time scales, of course. Okay, so what are these things? Well, as I mentioned earlier, in the late 60s and in the early 70s, many of these young stellar systems had been observed spectroscopically, and it was noticed that in the infrared regime, there was what's called the infrared excess. Many of these same systems also had an ultraviolet excess as well. I'm not going to discuss that. That's the process of actual bona fide accretion onto the star. But I'm going to focus on the infrared excess side of things. And the infrared excess is essentially a reflection of literally the flared structure of these young protoplanetary disk systems. So one of the main things that I want to take away from this is that the spectral properties and the scattering properties of the medium in the infrared range that has been observed is indicative that many of these systems actually have grains that are on the order from 1 to 10 microns in size. So we consider this as essentially the starting point for the assembly from micron size until, I'm going to point out, 100 kilometer sized structures, which are essentially the basic asteroids in which eventually the planets are essentially assembled. So essentially here's a basic disk schematic, and this is from a recent paper that came out by Testi et al. And essentially this is a donut structure, and when in the limit, when we're looking at a very young disk, the point in which we see light comes from that yellow region, as you can see over there. So essentially the last scattering point of the optically thin to optically thin transition in the disk. And so you can see here various places in the disk kind of labeled what can be seen in what wavelength range and so on. And the processes that are taking place, unknown to us, are taking place inside the zone where we can't observe directly. Although we might be able to see some structures associated with large bodies at the midplane of the disk in the millimeter range. And this is especially will be true when the gas of the disk has essentially dissipated. So the various processes here, I'm going to discuss them shortly, but I just want to give you a sense that essentially this is a narrative for how particles are grown inside of the disk. Now, there are many various narratives, and they all center on one of two things: whether or not the disk itself is turbulent or not, and whether or not turbulence is present in the places where the planetesimal formation and assembly is thought to be primarily taking place. And so this has been an open question. So before I get to that, let me tell you what are the problems that we face. Now, the meteoritic evidence is what we essentially go on, and cometary evidence as well. And so I'm not going to go into details of this subject because it's a vast subject, and it's something that I couldn't possibly go into, in an hour-long talk. But I want to kind of give you sort of a broad stroke picture. Essentially what we have are chondrites that are basically meteors, or large bodies of some sort. And inside these chondrite meteors are these inclusions of what are called chondrules. And the chondrules are these essentially small-sized grains, millimeter-sized grains, the ones you see here on the left. And they come in variety of flavors. The common ones, of course, are these pyroxene grains and olivine grains. These are essentially the founding members of the terrestrial bodies themselves. And there's others, of course, I'm not going to discuss here, but that's basically the idea. And of course, there are many subcategories of chondrules with a whole suite of empirical properties that are different from each other, and I could go on and on and on that, but it's not really the focus, so I can take some questions on it, of course, afterwards. Now, the chondrites essentially show evidence that they are essentially a collection of chondrules, but what's interesting is they're quite homogeneous. And I'll talk about that in a little bit in the next following slide. But the basic idea is that essentially they are composed of an admixture of all kinds of grains. And the origins of these chondrites can be anywhere from the inner part of the solar system all the way out to the outer part of the solar system. So it poses a very interesting issue. How do you form various grains that are usually specific to a location in the disk, and how do you get them to be mixed up throughout the entirety of the disk? And that's the question of turbulence comes in. Let me give you kind of a picture here. Now, this is, like I said, a very nuanced subject. I was at the LPSC last week, and I sat in on a couple of meteoritic sessions, and wow, I mean, the degree of knowledge and the kinds of subcategories that people are dealing with is mind-blowing. So I'm going to gloss over a lot of those points here, but I just want to kind of point out that in all of the actual laboratory analysis of these various chondrites show that the chondrules contained in them, the bulk chemistry, is essentially invariant across the metamorphic grade. And this is actually, this means to say is that the chondrules themselves, many of them actually show evidence of being heated and slightly melted. And when you take all that into account, and then you look at the whole sum total for a given object, you find that essentially all types are represented in a given chondrite itself. The other thing that's actually really important, essentially saying it's essentially homogeneous through all of the parent bodies. And what's also interesting is that a study done by Botke recently, essentially, or I don't know how old this is. This might be a little older than I'm indicating here. That essentially proposes that the actual parent bodies of planetesimals, the planetesimals that are that which actually made up the planets themselves, are probably about 100 kilometer scale structures. And this is based on a statistical survey of asteroids and asteroid sizes. And here's essentially, it's a point spread function, a distribution function as a function of size for the various things. So the takeaway bit here is, I'm going to read this bit out here, is that these factors suggest a primary accretion mechanism that carries on for a long time in situ, but in which each object accretes rapidly to the 120 to 150 kilometer scale diameter from a homogeneous but distinctive mix of chondritic components. And the only way that you can get these very distinctive small millimeter-sized structures to be spread all over the place is that there has to be, and I am contending, and we are contending, that there has to be some form of turbulence. Okay, so what's the big deal? Well, I'll get to that in just a little bit, so sit tight. So the evidence from the comets also indicate, and let me put it to you this way. One could say, well, okay, you could construct a process in which the bodies form outside at the outer parts of the solar system and they drift in. But we see from the evidence of comets, for instance, from the Stardust mission, that in fact we see evidence of comets which are presumably were formed in the outer part of the solar system also having these very heavy silicate structures in them as well. How did they get out there? So those are the constraints that we have to think about when we start constructing essentially this solar system cosmogony, if you will. So the point and the contention is an extensive amount of mixing is taking place. So so turbulence. Turbulence is a mess. And that's the whole point of it being called turbulence. Is basically it's the dynamics taking place in a very unsteady way, which is very hard to track from any analytical means. And so we are generally forced into either studying from a statistical point the properties of a turbulent flow, either from looking at data or studying fluid flow itself in the laboratory, or in the Earth, for instance, studying the atmospheric turbulence, or doing lots of numerical simulations. The takeaway point is the following. You can quantify the degree of disorder, I guess you could say, the whirliness of the turbulent state of a fluid using a very simple parametrization. It's not a good one, but it's one that is actually good for as far as our purposes are concerned in terms of modeling the behavior of dust particles in the presence of a turbulent flow without actually directly modeling the turbulent flow directly. So you can see here as an example, this is an example of a Magneto-rotational instability turbulence. And essentially what one does is you extract an equivalent what's called a turbulent diffusion or turbulent viscosity from the data itself. So essentially this parameter alpha is essentially it's a measure of the unsteady Reynolds stresses in the flow. And that's essentially a measure of how things stretch, turn, and deform on each other. And you can take a large numerical simulation and the thing will erupt for reasons which I'll talk about in a little bit. Well, I'm going to go through a series of mechanisms that cause it to erupt. But in the end, you can quantify this disorder by this parameter alpha. And it's given essentially as I say, as a viscosity coefficient, which is given as a product of some unknown parameter alpha, which is extracted empirically, and the sound speed, the local sound speed of the flow, and the local vertical scale height of the disk itself. So, great. How does one get to 100 kilometer scale structures? Well, as I said before, you can construct a narrative, we all are constructing a narrative, and that narrative is based on whether or not there's turbulence and how intense that turbulence is. I'm going to focus today on the issues surrounding the growth of these structures, assuming that there's some level of turbulence in a disk. So essentially, we have what it's called the early stages when you go from, say, micron scale objects up to millimeter scale objects. There's the process what's called sticking. And sticking basically is the process of, as you might imagine, dust particles float in space and they're being helped along by the gas, and then they find each other and they stick and they grow. And that process is quite effective at growing particles up till about a millimeter scale in size. But then we encounter a series of barriers to growth that takes us from millimeter to, as I called, the promised land, 100-kilometer scale structures. And those barriers are listed over here. The first one is the so-called bouncing barrier. And that, of course, and all of these barriers, where they actually become important, depends on the alpha of the disk. Of course, I didn't mention that. Now, the alpha in the disk can be a number anywhere from 10 to the minus 2 down to 10 to the minus 6. And 10 to the minus 6 means it's very weak turbulence. 10 to the minus 2 means it's very strong. But we're going to, these various barriers are assuming the degree of the turbulence is somewhere in between, 10 to the minus 4 in the alpha parameter. OK, so there's the bouncing, as I mentioned. There's the fragmentation. And that happens for larger scale objects and those objects are being carried along by the gas, and they're bouncing around. And if they get too big, they can ram into each other and then completely fall apart. And you don't grow anymore, you break down. So that's one. The other one, it's what's called the drift barrier. Now, this is an interesting thing. I will talk about, you'll see this more clearly in a follow-up slide. But essentially, it's the following. When a particle grows large enough, it encounters gas drag. And that gas drag, or the gas itself, may be actually in what's called pressure support around it's rotating around the central star. It's under pressure support. But the particles themselves, if they get large enough, that gas drag becomes important to the degree in which particles start to drift past the gas itself. And in doing so, the particles get their angular momentum robbed from them. And in robbing the angular momentum causes the particles to eventually it could be very quick, several orbit times, spiral into the central star itself. Because if you're constantly robbing it of its angular momentum, it's going to do one thing, it's going to spiral in. OK, so that's not good. You could say, well, why not? Why isn't that happening? Well, we know that these things survive to a long degree of time. And we're having mixing. That last thing we need is drift, that kind of drift into the central star. Now, there's turbulence enhanced growth, turbulent enhanced gravitational scattering. That's actually happening on a larger scale. And that's essentially the following. You can imagine it's gravitational scattering of largish structures. Here, in this case, 1 to 10 kilometers in size. I mean, it's enhanced by the fact that the gas is actually pushing them along. And when particles interact with other particles, they start to feel their gravitational tug, and they scatter off. Question is, can we avoid all of this? And that's essentially what's called the barrier leapfrog mechanisms. There's actually several more than what I'm going to discuss today. But I'm going to talk about the two that I think are most relevant for the disk. For disk particles. One of them is the following. It's called the streaming instability, and this had been kicked around by theorists for the last 15 years or so, and essentially is a process in which requires that the gas and the dust mean densities be about the same. So it's a very late stage in a disk evolution, and then once that's the case, there is essentially, you can kind of think of it like an aerodynamic drag effect, in which, kind of like you see here in these the Peloton kind of scenario, where you get a group moving, and because of the aerodynamic drag that is actually, there's another nicer way to say this. Individually, these particles, the cyclists, won't be able to move as quickly when they're faced with having to overcome the gas drag of the air flowing around them. But if they come together and they're brought together, they actually move faster as a group. And it's essentially kind of the same idea. There's a bit more physics involved in it, but essentially it has to do with kind of mass loading the flow that you're in. And by doing so, you can attract other particles into your kind of trajectory. And in doing so, the group can actually move forward. So this is a nice way to get a bunch of particles together and to grow to larger sizes as a group. And eventually, presumably, these will then collapse on themselves. The problem with this is that it requires that the solids, as I mentioned, the density of the dust to be significantly greater than the density of the solids. And this is hard to do if the medium itself is quite turbulent. Imagine trying to get this Peloton thing to go in an effective way if it was really windy, gusting all over the place. You can imagine it would be kind of harder to actually form those, such a coherent structure. Here's another mechanism that can actually get over the barrier, and that is what's called turbulent concentration. And this is kind of nice, and this is stuff that a number of people have been working on, including my colleague, Jeff Cuzzy. And essentially what happens is the following. If you have a turbulent medium, now I'm not telling you where this turbulent field comes from. I'm just saying, let's say there's a turbulent medium. And it turns out that particles, small individual particles, and this is based on laboratory evidence and data analysis, little particles try to avoid locations of high vorticity, meaning locations where the change in the swirliness of the flow is minimal. So that could be actually in the middle of a vortex, sort of like the eye of the storm, or in places where the vorticity is minimum, say away from vortex tubes in the field itself. So you see here on the left is an example of what happens to particle concentration in the midst of a vorticity, strongly turbulent strongly turbulent medium, and the particles always find the minimum location of where the vorticity is close to being zero. And it makes sense. It wants to be in a place where it's nice and calm. Doesn't want to get too ruffled up, as it were. Now, of course, this requires that the turbulence be present but somewhat moderate. You can imagine there's a sweet spot. If it's too violent, then you don't grow clumps. Here, the middle one is a kind of a nice image here where it actually shows an example of a turbulent flow field taken from atmospheric data being used as a seed. And then what they do is they drop particles in it and they watch how the particles evolve in that flow. I'm not telling you where this, in this particular case, this turbulent flow comes in the atmosphere, but for the disk, I haven't discussed where that comes from yet. But you can see when you go from the left to the right image there, the dots just essentially tell you how the particles cluster in that configuration, in that state, in a sense. That's all very nice. So what I haven't answered, of course, is what is the nature of turbulence in disks? And that's going to be the second half of this talk. So let me just kind of give you a bit summary here of kind of where we're at and essentially where we need to go, or what are the constraints in our thinking. And that is, essentially the parent bodies of planets are essentially 100 kilometers in size. The evidence suggests that the chondrule grains of various compositions, that suggests they were composed of chondrule grains of various compositions, suggesting that both radial and vertical mixing in the disk has taken place. Here's a nice analogy. I neglected to mention this before. The picture is, when I go back to this question of the grains, it's like you take, a nice analogy is, let's say you're at a beach and you got all this sand. And you know that the sand is composed of all these different grains of all these different types. And you know over there's a big mountain. It's a volcanic structure with obsidian and all that good stuff on one end. And then on the other end, you see that there's another mountain composed of, I don't know, some kind of granite, silicate structures of some sort. And then maybe there's a third mountain composed primarily of metamorphic rock of some sort. Those essentially are the sources of the sand grains that you see down, let's say, at the beach. And they were transported there. So in a sense, the origins of the individual grains are these mountains. The transport brought them together to make the sandy beach. And the sandy beach, the analogy is those are the chondrites themselves. There's a transport mechanism. And for me, that's the way that I like to kind of think about this problem when trying to explain it to other people and also trying to make rationalized sense of it for myself. There are several mechanisms to leap over barriers, these various barriers that I mentioned. They each have their own problems. The turbulent concentration, I glossed over this a bit too quickly, but the turbulent concentration works only if the particles themselves have grown to about a centimeter size or more. To get there, you still have to confront these other barriers. So if you start with millimeter-sized particles, you can actually grow clumps that are on the order of, say, 10 kilometers in scale. So the problems still remain, and so this is currently an active area of research, and one of the ideas that had been proposed is that perhaps under those conditions, we have a situation in which the streaming instability is operating together with the turbulent concentration, kind of in concert to get over that last bit. We don't know. These are things that are being currently examined. All right, so let's get to the good stuff as far as I'm concerned. Turbulence. So protoplanetary disks and the turbulence within them has been a subject, like I said, of intensive research over the last, I'd say 50 years, but very intensive from the vantage point of numerics in the last, I would say, 25 years or so. When I basically started graduate school is when this work really, really took off. And a lot of the people who were pioneers in the original early studies in this were folks here at NASA Ames Research Center at a place called the Center for Turbulence Research, and there was several folks working on that problem there. I just wanted to show you this, kind of revisit the picture. And one of the things I want you to kind of keep in mind here, it's not going to bear directly on what I'm going to say, but that disks also have a tremendous amount of non-trivial structure in them. So whatever is happening is also giving rise to this asymmetric sort of features that we see, or slightly asymmetric. Obviously, in the ALMA image on the right, it looks pretty it seems pretty radially symmetric. But there is, of course, as you can see, there's mild structure in place. And a recent, wow, that Cassasius came up twice. Sorry about that. In this other image is kind of another accretion, a protoplanetary disk itself. Also shows evidence of enhanced either mass loading or thermal output, and you can see clearly a non-axisymmetric component to the structure that we see here. So that's basically something to think about. So what's so strange about disks? So disks are essentially these objects in which you have to find a way to get essentially mass to transport in towards the central star, in general accretion disk structures of one form or the other, because there is some mass transport that's occurring. In order to do that, you have to shed the angular momentum, and the primary way in which radiation comes out is in the disk vertical direction. And most interestingly, most of the kinetic energy component of a disk is contained in flow, which is essentially here kind of perpendicular to all the vectors seen into the page, for instance, in this context here. So this is a system that's both strongly sheared, and all the directions are very important in the sense of the dynamics that are occurring. And in astrophysics, we only get these two kinds of limiting forms. You either have nice, perfect spheres in which all the pressure gradients, all the motion, and all of the activity is taking place more or less in the radial sense, with some sort of fluctuations around that. But disks are places in which the pressure support is dominated by the rotational action, so we call those rotationally supported, and they eventually result in these pancake structures. And as I said, you only get these in two flavors, basically. Okay, so turbulence. So there are many ways to get turbulence in a medium. There are many scenarios to the transition to turbulence. And I'm only going to focus on the classic scenario. It's the classic scenario associated with what's called the Richardson cascade. I'm sorry I don't have time to talk about the other stuff, but I'm speaking about these because we think that these are probably, this route to turbulence is probably the one that's relevant to accretion disk, especially given the new results that we have in terms of their, turbulence mechanisms. Essentially, it goes like this. You have large vortical structures, top row here. Those come about through some means, some instability in the system of one form or the other. Those large vortical structures eventually undergo a secondary transition into breakdown. Essentially, those large structures break down into smaller structures, and essentially we call this essentially a cascade effect. And that secondary structure itself may or may not be unstable. In some cases, the primary structure leads to a secondary structure, and the game is over. So it's no longer really turbulent. It's just a very complicated flow state that's otherwise quite laminar. But typically, it's that secondary structure undergoes a secondary instability, and then it runs away. Because as the secondary flow becomes unstable, it leads to new structures that are even more and more and more complicated and are susceptible to other kinds of flow instabilities. Now, that's a broad stroke picture. The state of turbulence right now is trying to pinpoint what all these various things are for a given type of flow, which is why there are thousands, tens of thousands, 100,000s of people around the world over the last 50 years have been studying this problem, because it's no way to extract a uniform picture from the large structure that's driven into place down to the smallest scales. And the smallest scales are the scales in which that energy that's driving the large scale structures in the disk or in the flow eventually cascade down to the dissipation scale, and that dissipation scale is the actual molecular viscosity scale, and then dissipated, it comes off dissipated in the form of heat, generally speaking. So there's this stage. There's the driven stage. There's what's called the inertial range. The inertial range is everything in the middle here, where it says the flux of basically the energy. And then there's the dissipation scale down at the base. Okay, so, well, what's the source of turbulence in disks? Well, for essentially the last 20, 25 years, it had been supposed that the source of turbulence in disk is a mechanism called the Magneto-rotational instability. It requires the disk to be sufficiently ionized for magnetic effects to be important. I'll show you a very quick and dirty way of understanding how this instability operates. But what's critical here is that the degree of magnetization of the disk is essential here. There's no magnetic effects at play, at least so it was thought. Disks, despite being strongly sheared, were not obviously unstable to some kind of turbulent. I'm sorry, let me say it again. Despite the fact that that disks are strongly sheared objects, where the flow is moving past each other with a great deal of intensity, that did not obviously lead to some kind of mechanism in which you have an instability which would lead to that first level of vortical production. And a lot of people looked at the problem, and it's a bit of a mystery why we didn't figure it out back then, but it wasn't the case. So I'm going to talk about actually what they are in a few moments. So that's the exciting thing. That's the thing I'm kind of excited about, because I've kind of been involved in that story as well. In the case of the magneto-rotational instability, this schematic is quite nice. Basically, the idea is the following. You take, here on the left, you have two particles undergoing a circular orbit around a central object. They are actually physically sheared, as you can see by the next time step there. You see that the two particles move past each other. And I'm speaking of particles, could be fluid elements, could be whatever you want. If there is no meaningful coupling between the two, this is just going to go on and do its dance in the way that it wants to do it. However, if there is any kind of coupling, let's say a spring. Imagine you put a very weak spring between the two of them, a slippy spring. That slippy spring will do the following. It will actually, as you can see on the top left there, that slippy spring is going to actually pull that particle back a little bit, slowing it down. But in doing so, you're actually physically robbing it of its angular momentum. And in doing so, that particle is then going to start to slowly swirl its way back in. It's very similar to the idea of the drift instability associated with particles themselves. Similarly, the spring will actually give a kick to the particle on the outer part of the orbit, And in doing so, it's giving it its it's gaining angular momentum. And in fact, the inner one is giving its angular momentum up to the outer guy, and he, not mean to anthropomorphize, or she, or she, will spin away slowly as well. That's a runaway process. In the case of, so that's basically the idea. In that case, magnetic fields in this case can offer that springy action. Here's an example of where the spring comes from. In this case, it's the example in which this was actually originally identified as being relevant to an accretion disk. It turns out Chandrasekhar and Velikov back in 1959 had understood this to be an instability as well, but in a sheared flow. But it wasn't until 25 years ago that Balbus and Hawley first identified this as being relevant for a disk. And essentially, the magnetic field lines are the source of the connection between particles. And if they're take two particles that are slightly raised from each other, and then they communicate with each other in the fact that the magnetic field lines get stretched and pulled apart, but in doing so, tries to pull them back, but in doing so, robs each one of them of their angular momentum, and then you have this spreading effect kind of going on. And then, so that's basically the idea. So as of, I don't know, say 4 years ago, 5 years ago, the consensus was that accretion disks themselves, protoplanetary disks themselves, are primarily magnetically active, and the source of turbulence in them is by this mechanism. But there was this problem. Oh, you can see here, like here's that picture I showed you earlier, this one. This is the look of the flow as it gets rendered unstable. But there is this problem. It's the problem of what's called the dead zone. The dead zone is a location in the disk where the magnetization, or the resistivity of the disk is so high that the magnetic coupling to the flow is almost nil or entirely absent altogether. So it was actually identified, this region had been identified as being unstable, as being present about over 10 years ago. So it was called dead. And I think that was unfair. Because what we have found is that dead zones aren't actually dead after all. And this is work that has essentially been uncovered in the last 3 to 4 years. And essentially what we have here is various number of instability mechanisms, the primary scale instability, the corresponding secondary mechanisms that are present, and then all of these and all of the numerical simulations that have been done, and I'm going to show you some of those results now, result in essentially a downscale entropy cascade. So the rest of this talk, about 10 minutes, I'm going to kind of go through and show you get kind of the flavor of what this looks like and what the states that result are. It's really kind of exciting. This one I was directly involved with, and it was totally by accident. It was like my last week at Queen Mary University. I was a postdoc there, and Richard Nelson came into my office. I was working on other problems, and he's like, I'm running disk simulations, and I turn off the magnetic field because I want to see what the particles are doing, because I want to see how the parts of the disk that are driven by MRI turbulence is churning up activity in the inside. And I'm finding that when I turn off the magnetic fields altogether across the entirety of the disk erupts. And I keep thinking this is a numerical thing, a numerical artifact, and so on. And I looked up, I don't know. I had no idea what this was. I had no clue whatsoever. And so I was office mates with another fellow named Oliver Gressel, and this is the end of 2011 and 2010, and we started to hammer at the problem, and we got it wrong 4 times. We had no idea what it was we were looking at. It was one of those, it was so bizarre. Here's what it looks like. This is essentially a cut of a radial azimuthal cut across the disk. And what's plotted here is the vorticity. For the people who are technically inclined or are interested, I've left the words up there to discuss. I'm going to just kind of talk here basically what the basic mechanism is and what it looks like. You see that eventually this disk configuration erupts into this vortical pattern, and it's very mild, but it's persistent. It requires one thing only, that there's a radial temperature gradient in the disk. That's not an outlandish thing to suppose. In fact, we know that from very basic considerations that protoplanetary disks have radial gradients on the scale of the disk radius itself. On the right, you see what the flavor of this instability really is. The right shows you the vortical pattern, which is also similar to the velocity pattern as well. And essentially what happens to the disk is that the flow begins to go up and down, kind of like knives going like this, and it erupts. And it has a turbulent response, which is relatively strong, but not zero. And the origin of this has to do with the fact that the radial temperature gradient induces a shear of the Keplerian flow, not just radially, because you have one radially because of the central star, but you have a shear vertically as well. So the mechanism is actually quite simple. The mechanism is the following. This is a class of instabilities that's associated with the Taylor-Couette instability. And these are famous experiments that are done in concentric cylinders. And the way one assesses whether or not this configuration is unstable is you take two particles and you interchange their positions. And then you ask the question, if I interchange their positions and have them conserve their angular momentum, okay, is the final state lower in energy or greater in energy than the original configuration? Now, normally, accretion disks, protoplanetary disks with Keplerian velocity profiles, when you do this, you actually examine the interchange configuration radially. But if you have a shear vertically, then that means that there will always be some point somewhere up in the disk when I interchange their positions radially and slightly vertically and radially, that final configuration will be of lower energy state. And that's it. It's that simple. And it's the reason why, for instance, I can see there, that's kind of the schematic here essentially kind of summarizes that. So the reason why you see that the instability primarily manifests itself as very small radial length scale structures and very strong vertical oscillations like this. And it's persistent. Now, there are conditions in which this is and is not going to operate. I don't unfortunately have a lot of time to talk about that, but I'll get to that at the very end. The secondary instability is nice, and it's called the Rosby wave instability. So many of these, if you look closely, you see that essentially you have places of positive and negative vorticity, and the places of negative vorticity end up actually rolling up on themselves. So first you get these blades going up and down like this, and eventually you get this secondary instability manifesting itself in a direction which is symmetry breaking. And that's one of the things I should have mentioned earlier, and is very essential for turbulence, is that generally speaking there is a mechanism that comes about that brings the primary structure into place. The secondary instability, if it's going to trigger turbulent cascade, is usually a process that breaks the spatial symmetry of the primary structure. So generally speaking, that's what you look for. You get your primary structure may be axisymmetric, and then you look for the secondary instability, which would be some sort of structure, let's say, that has structure in the vertical direction, as an example. Always some kind of symmetry breaking is taking place. Bring this sort of thing about. So that's the case here with the Rosby wave instability. Basically, here you have essentially what's called a shear layer, and we see shear layers all over this structure here. And that shear layer can actually undergo a secondary instability, and it's basically what you might say in the simplest way, it's like a Kelvin-Helmholtz roll. But the shear layer itself will undergo a roll, an instability, which actually turns out is a function of, is a result of the interaction of Rosby waves. And meaning to say, Rosby waves, sort of like the jet stream pattern in the atmosphere and the Earth, is essentially a pattern of that's reflective of the fact that it's a giant Rosby wave propagating westward on the planet. And essentially, that's what you have here. On the top is an example of a Rosby wave, and essentially you take a fluid surface which is level and you undulate it. But this fluid surface below is sheared and above it's not. It's a great theoretical construction. When you undulate that surface, the vorticity itself is literally carried by the fluid elements themselves. But that undulated surface responds to the fact that it's spinning in a way that causes the pattern to drift, in this particular example, to the left. So any Rosby wave will exist on a material surface in its rest frame and always drift against essentially what we call the gradient in the shear. The bottom bit here has a shear, the colored bit is sheared, the top bit is not. But if you have two or more surfaces which can support Rosby waves, and they themselves are boosted by some mean velocity field, you can get these Rosby waves to become phase-locked. The minute they become phase-locked, they overturn, and they form vortical structures. So literally, this shear layer, the conditions are right, will overturn and break down. And essentially, that's essentially what we see here. This is a very violent example of that. It's one of my simulations in which the shear layer is broken down, and then you see a rapid cascade of power to the smaller and smaller and smaller and smaller scales, which is cool. I mean, I think it's cool. I mean, I like this stuff. So, okay, wow, 5 minutes to do two more mechanisms. This one is, I'm glad I spent the time to develop those two, because the other ones can be spoken of in kind of in using the language I just developed a few moments ago. This is a mechanism also developed by Phil Marcus and his team here at Berkeley as well. And essentially what they find is this, what's called the zombie vortex instability. And it's a funny sounding name, but essentially it's the following. If you start with a seed, and this is again a simulation, a local simulation of a disk, where you have the radial and the azimuthal section, and that's a similar cut of the same panels, but radial with vertical. And you start with a seed vorticity field right there. That can then cause a spread of itself across the whole domain. It's odd. That's why it was called zombies, right? Because this is in the days when we thought disks were dead. And, oh, well, disks are not dead. They're coming alive. Essentially, it's just spreading. It's like an infection that's spreading across the thing. What's the cause of it? The cause of it is the following. That seed vorticity field, wherever it came from, will have a Rosby wave associated with it. But what it does, it actually triggers a response far afield from it, say here, which is actually a resonance. And get this, it's a resonance between a buoyancy oscillation in the disk. It's a buoyancy oscillation in the disk at some distance away from the primary vortex field, and the Rosby wave that's Doppler shifted. So basically, you take a Doppler shifted Rosby wave. It has a frequency associated with it as viewed at that far field point. And if that is resonant with the buoyancy oscillation of that location of the disk, that will erupt. It's called a critical layer instability in this particular case. And the beauty of it is that it drives into existence another jet or another shear layer. That jet shear layer grows, and it does the same thing downfield. So it spreads. It overtakes the entirety of the domain. That shear layer, in and of its own right, will undergo a Rosby wave instability. It will eventually break down. So the idea is that this is, whether or not this is sustained and for how long remains to be seen, but it looks like it's a bona fide mechanism to drive that kind of activity in a disk. So which is why, if you noticed back here, when I was talking about the various instabilities, zombie vortex instability gives rise to more zombie vortex instability. So it's kind of a back and forth thing, but that can also lead to this nice Rosby wave instability. Okay, so I got you for 2 more minutes, and then I'm going to wrap up. Sadly, my exuberance is taking over. I do apologize. This is one that is actually pretty nice, and actually I think is probably pretty relevant. The short of it is that it turns out that a disk with a radial temperature gradient can also undergo a buoyant instability, much like convection when you have a layer heated from below and cooled at the top, and you can cause buoyant oscillations to rise and overturn on themselves. But the problem is that it was thought that in a disk, that ought not happen, because there's also this other added feature that disks have an epicyclic frequency associated with it. So motion will actually, that type of motion will be interfered with by the fact that the disk itself is going to oscillate back and forth associated with its epicyclic oscillations, associated, let's say, with various inertial waves in the system. So it had been ignored as a possibility, and most of those calculations that had been done, or examinations were done, had been done assuming that the instability, the disturbances were primarily in the radial direction and the azimuthal direction. But it turned out, and this is actually a long story because how we got here, but the short of it is, turns out that Hubert Klar used to also be here, and Vladimir Lira, who's down at JPL, they re-examined the problem and showed that, in fact, as long as you introduce vertical perturbations to the disk at the same time, so this is a bona fide three-dimensional instability, which is very different from the other two in a fundamental way, that can erupt, take a disk section, which we have here, and eventually turn this into essentially a roll that's turning on itself, with the vorticity pointed in the vertical direction. It undergoes secondary instabilities as well. Now, you would think if it goes through a secondary instability, what is it? And when it breaks down, ought it not completely shut itself off? Well, it doesn't. Let me tell you about the secondary instability itself. This was done by work by Popoloizou and Lesueur, and back in 2010. The references are at the end here. I forgot to put the name up. The Popoloizou and Joffre, who's a friend of mine, they took an elliptic vortex and they stuck it in a disk, and it's like, does this last for very long? If it does or does not, let's figure out what's going on with it. And they found that all giant elliptical vortices that are embedded in a disk will ultimately collapse on themselves and break down. And that's exactly what you see here. And you can see, in fact, that vortex has a three-dimensional instability associated with it, and it collapses, and it falls apart. So normally, in the absence of anything else driving that vortex into existence, that vortex is gone, everything calms down, all the vorticity is shed, everything is done, everyone goes home. But you don't in this case, because the primary instability mechanism is still operating. It's that buoyancy instability. It's going, and it's driving into place that vortex, which is why this looks so messy looking, because it's actually that turbulent. It's quite violently turbulent. So that's the short of it. I wish I could spend a little more time. I got 2 more minutes and I'll wrap up here. So essentially, where might this be acting? Well, turns out that all these mechanisms act essentially in places in the disk, at least from the linear side of the problem, in places that are exclusive from each other. So places in a disk that were once considered dead zones, now it's kind of like a cutlet of beef, right? Various sections, different types of instability mechanisms at play here. And they're essentially exclusive of each other here. This is a radial vertical cut scaled by the vertical scale height of the disk. And what dictates the presence or absence of a given instability has everything to do with the opacity of the disk. So now that's where all the work that we are doing is trying to essentially now work out how does the opacity, so in other words, if the disk is optically, well, let me rephrase that. If the disk locally cools on a time scale that's very short compared to the rotation time of the disk, the vertical shear instability is operating. The other extreme, where the cooling times are very long compared to the rotation time of the disk, this zombie vortex instability operates. And right in the sweet spot where there's neither large nor too small, the convective overstability mechanism is operating. So based on this current picture, which is actually this year, maybe we're dealing with a situation in which all these things are operating at the same time. The dead zones are not dead. They have risen. No. They're active. So thank you for your time. I'll leave the summary up here, but let me just quickly go through the main point. So I think the big leap forward has been made, and I think we have now clearly identified that these regions in the disk are truly active. These processes have all been independently confirmed by several independent groups in the last 3 years, because it's that important. Because before that, we were like, oh, nothing's happening. Oh, something actually is happening, and it's probably happening all over the place, better than we thought it would be, more effective than we thought it would be. And the important other fact that comes from this is that the turbulent intensity that comes from each of these mechanisms is generally enough to provide the kind of mixing that we think is likely to be happening in the planet formation, assembly, particle growth phase of many disk in the disk evolution. So there are other issues that need to be addressed, and I'm not going to get into them right now. But essentially, the one that's really critical now is how does the disk opacity change when you start changing the distribution of dust? Because the distribution of dust particles affects the opacity of the disk, and the opacity affects the cooling times of the dynamics in the disk, in the gaseous part of the disk. And so how does that feedback mechanism affect what's going on the largest scales? That's kind of an area of active research right now, but I'm just kind of happy to be part of this story. So anyways, thank you very much for coming and listening to my talk. And
All right, thank you very much, Orkan. We do have time for questions. Please raise your hand and wait for the microphone to come as we are recording.
Hi, Orkan.
hi, hey, nice to see you.
Yeah, good to see you too. Nice talk. I have a question. Like the planetary rings, like on Saturn, from what I understand, they're not all that turbulent. Why are protoplanetary disks so different from planetary rings?
It's because planetary rings have very little to no actual gas in them. So those are basically, it's literally a ring of particles that have very little interaction between themselves. In a disk, you have the gas. That's the medium in which everyone's talking to each other with, and the dynamic interaction is happening through that medium. Don't hurt your hand.
No worries. How dense is the gas, like compared to, say, one Earth atmosphere or something?
Oh, much, much, much less. much, much less. Some of those numbers are kind of running off. I mean, for these accretion disks. Oh, one of the things you need to understand is that in the protoplanetary disk, the gas over time either gets blown out of the system or swallowed up by the planets, or gets incorporated, swallowed up by the star, or gets incorporated on the planets themselves. So it's a process in which the density is steadily dropping over time. I didn't include that in the backdrop here, but yeah.
Yeah, that picture that you had for the convective overstability, the thing that looks like a block, a 2x4.
This, yeah.
Yeah. Or is it a 1x4?
It's probably a 1x4, and that's the knot.
That knot in it is so reminiscent of Jupiter's big spot.
Yeah, isn't it?
Or what used to be a big spot. Is that a coincidence or just an optical illusion or what?
It's been discussed that Jupiter's red spot is actually a giant geostrophic vortex, but it's driven into place by some thermal instability or some thermal process happening deep down in its base. I think the similarities are there, but whether or not that mechanism that's driving that into place is the same here, I couldn't answer that. I'm not sure. It's possible. You know who would know? Be Professor Phil Marcus at Berkeley. So I highly recommend you invite him to give a talk as well.
I've got a question about kind of the very, very beginning, when I presume, I don't know much about this kind of thing, but I presume it was all gaseous. So you had gaseous silicates before you had any solid.
Right.
And so what were the temperatures and pressures? What were the dynamics there? And then the condensation producing solids would inject a lot of energy into the system. Does that have anything to do with, it seems to me it can have a lot to do with the sort of thing you're talking about.
Sure. I suspect, in terms of my understanding of these processes from the gas dynamics side, you expect that there should be an energy injection into the system when you have, say, condensation shift, going from, like, say, water vapor into the ice form. How large a component and where that radiation goes does it stay trapped in the gas itself, and it depends on how thick the gas is and where that's happening, of course. But from some of my calculations that I've done, the energy injection is still a very small component of the total gas, the density, the energy in the thermal energy of the gas itself. That fluctuation. So that's one of the things we were looking into, is that it's possible that you have an ice line forming and that can then drive kind of instability into place. And some people are actually looking at that problem. And in fact, you could drive a Rosby wave instability in that system. The edge of the ice line is a source of energy gain loss. But the question is, it all depends on what are the opacities that we're dealing with. Is that radiation lost? It stays trapped in the disk. So that's one of the things that we have to, and all of these things affect what the opacities are going to look like and where. If you have large particles being kicked up into the disk, then certain parts of the disk have very high opacities and certain parts of the disk are going to have very low opacities. Right now, most of these formulations assume a sort of a vertically uniform opacity picture. But now if you have all these dynamics, that's going to start to change. So that changes whether or not this radiation is trapped, at what level is it trapped, and stuff like that. So yeah, I wish I could give you I'm going to say yes. The answer is yes. It's going to affect things, but how it affects right now is not entirely clear. But we have some ideas. Yeah.
I'd like to ask a question about the earlier part of your talk, where you were talking about ionization and magnetic fields, and the magnetic fields might, in fact, cause interchange of material and turbulence. In one of your early figures, you actually showed the ionization in the disk due to galactic cosmic rays. The thermal ionization is this is the figure. Thermal ionization is so important close into the star. I'm a little bit surprised with my understanding that galactic cosmic rays in the outer part of the disk had essentially produced so little ionization, so little conductivity, that you couldn't generate a useful or significant magnetic field. Is that correct?
I was under the same impression, but recent work in the last 2-3 years have kind of re-examined this question, and they are suggesting now that in solar type disks that this ionization is going to be significant out to as close in as 20 AU. Yeah, that was news to me as well. I'm not an expert in that particular calculation, but yeah. And this story goes back and forth. Another paper comes up, like, no, you guys are wrong. No, you guys are wrong. And you know how it goes. You're trying, because you left this bit out, left that bit out. But currently, the general consensus is yeah, it ought to be active at least out to about, as close in as about 20 AUs or so.
That's quite different. Thank you.
Very different, yeah.
Any others? All right, well, I would like to conclude by presenting Orkan with our famed SETI Talk mug to token of our gratitude for coming here. Let's thank Orkan Umurhan one more time.
Thanks. Thanks a lot.